my slides drop out, just let me know. So thank you, Henry. Thank you for the incredibly kind introduction. And again, I just hope I can live up to your words. So as Henry said, we're going to talk about the Smart Grid Framework version 4.0 today. I am the Smart Grid Program Manager at the National Institute of Standards and Technology. And through this talk, I'm going to begin with a little bit of a description and introduction of NIST for those of you who may not be familiar with the organization or our research program. Then I want to dive into the framework. And I'm going to finish off. You see those light blue things at number 5 and 6. These are the areas where the framework has some really important outcomes and next steps. And so we're going to dive into those, the issues of cybersecurity, as well as interoperability profiles, which is something the framework proposes to really advance smart grid capabilities. So, right, what is NIST? NIST is pretty old, and from the start, we've been focused on helping things work better for the American consumer and industry. We've also been involved with standards for the electrical industry from the start. You can see this, very old picture looking at how light bulbs work and their light output. Our mission today is to use measurement science to inform standards and drive technical innovation throughout the U.S. economy. So an important question is, why is measurement science the first thing we talk about in a chain that leads to driving innovation? NIST believes that you must first be able to measure something before you can optimize it. And because without that measurement, you'll never know if you made an improvement or not. So in short, measurements are the foundation of both the problem statements that describe the work that needs to be done, that quantify the gaps, and measurements are also the way we assess the value of the new technologies that solve the problems we face. Measurement has been a part of what government does from the very beginning, and measurement combined with technical standards are critically important to all forms of commerce, the electric grid included. So why is NIST doing the framework for smart grid interoperability? The short and easy answer is because Congress told us to. And here's some words from the Energy Independence and Security Act of 2007 that instruct NIST to do some things. But I happen to think these words that I've highlighted in yellow are the most important points, right? Our job is to modernize the grid. We are not doing this to just simply keep the old grid running. Another point is that NIST is supposed to coordinate the development of the framework, not write it in isolation. So we work with stakeholders and contributors across the power sector and use their input to inform the ideas that we express in the framework. The third is that the framework must focus on enabling all electric resources to be part of the solution, right? We have no magic bullets here. And I want to emphasize the point of coordinating here, right? That's why I'm here talking with you. We are in the public comment phase of this framework, and I hope that after we're done with this conversation, you'll head to the website, download the report, and send us your comments so we can consider your input along with the other public comments we receive. I also want to highlight this word interoperability, right? This is what we're focused on. Our framework is geared to improve and manage interoperability in the grid moving forward. So this version of the framework is a wholesale revision. While the current framework is founded on some similar foundational concepts to earlier versions of the frameworks, we use these concepts in completely new ways in this version. And those new ideas are reflected in the content and chapter structure. And I think that's a good thing, right? Because technology is advancing rapidly, and the ideas about how we would use and communicate information in the grid are not the same today as they were 13 years ago when the Energy Independence and Security Act was passed. So with all that background, right, what exactly is interoperability? We have our definition in the upper left-hand corner, and that is important. But conceptually, I think the most important thing to understand is that interoperability is a tool for unlocking new value across the power system. That value can come from improved operations and efficiencies, avoided costs due to decreased outages, or integration of new resources and economic opportunities into energy markets. So in fact, as our grid modernizes, the opportunity to gain value from interoperability grows with every new data stream or communication action. The Gridwise Architectural Council estimated the US power sector could save $10 billion each year through improved interoperability. But we heard at our testing and certification workshop in 2018, that was the first time we rolled out some of the ideas in this framework, that a single equipment manufacturer spends $1 billion a year on integrating non-interoperable devices into their R&D laboratories. Now, those costs are passed on to the consumers, the utilities that purchase their equipment. And a single IOU or investor-owned utility spends $140 million a year trying to get new but non-interoperable systems to work together. So put in those terms, and when we consider the economic opportunity each customer can embrace by integrating their technologies and resources into the system, the value proposition may be much higher than we ever previously thought. So the traditional utility approach to interoperability is to decrease the integration costs for new equipment. EPRI even published a paper on this in 2017. And to be honest, while the paper is very good, I think it's a low bar for the value of interoperability. And amazingly, reducing the integration costs for utilities is a benefit that is actually undermined by the typical utility revenue structure, because utilities are compensated best for capital expenses. And when integration costs are folded into a procurement, the cost of overcoming non-interoperability between utility systems actually becomes a profit maker for the utility. So the structure of a typical tariff, which compensates utilities more for capital expenditures than for O&M, creates an incentive for utilities to keep their equipment integration expenses high. Now, I am not saying that this is what utilities prioritize. I am not in any way saying that utilities intentionally buy things or systems or equipment that are difficult to integrate so that the costs can be raised and they can be compensated higher for their capital expenditures. I'm not saying that. But what I am saying is that the revenue model for a typical utility doesn't provide an incentive to actually improve interoperability because of the way that they're compensated. So now contrast that to how interoperability enables consumers to pursue any number of value propositions. By managing their energy consumption and contributions, consumers can pursue environmental benefits, financial benefits, resilience benefits, and improve their ability to develop new opportunities through collaboration and coordination with others. These value propositions are indicated by these various circles on the right-hand side of the screen. These all require information exchange. And so interoperability empowers consumers to seek and develop their own value-driven priorities. But in this quest to interact with others, interoperability does something more. It's about more than exchanging the typical energy demand or billing data. It's about unlocking the physical capability of equipment to do something more than it was originally intended to do. So let's consider the thermostat, right? The purpose of a thermostat is to control the temperature in a room by actuating an HVAC in response to measured temperature changes, right? That's it. It is specific in what it measures and how it works. Now consider the communications-enabled thermostat that is interoperable with other systems. That thermostat can be used to manage distribution system congestion, thereby preventing circuit overload and improving system resilience, or that thermostat can be used to clean our environment and balance variable generation renewables, timing its on cycles for when carbon-free power is available. Or that thermostat can decrease heating and cooling costs by pre-cooling or heating to avoid peak rates. And if we think about utility equipment, interoperability is a hedge against obsolescence. So equipment that lasts extra long also tends to be extra specified, making it even more challenging to have that equipment do anything other than what it was originally purchased to do. Just as consumer equipment benefits by breaking asset specificity, utility equipment can be more versatile and work longer under different operating conditions by enabling communication. Using standard communications protocols to support interoperability therefore decreases the likelihood that still functioning equipment will become either a stranded asset or a reason to avoid system upgrades. And so it is in that context that we updated and expanded our conceptual models for the smart grid. These models help us think and communicate about the smart grid, both where we are and where we need to go. I want to point out that while the conceptual model had modest updates, the communication pathway scenarios and ontology for the grid are new tools for this version. So here you can see the smart grid conceptual model, which has been consistently updated with each framework. The important things to note here are this. So there are 7 domains of the system, which allow people and organizations to understand where they exist physically within the system and with whom they must interact. The power flows indicated by the dotted yellow lines appear relatively simple at this level, and the communications flows indicated by the blue lines needed to operate and optimize the system are very complex. I got to be honest, the few linkages not shown here were merely an effort by me to enforce something more meaningful than an n-1 complexity diagram. Some changes to this version are more automation, sensing, and control in the distribution domain, diversification of generation, including DER domain, and an elongation of that domain so it can graphically represent the physical proximity of certain resources to different portions of the system, and customer diversification. Interestingly, though, there's not much new about the customer domain. All the new graphics for the customer domain at this level merely raised the information that was already described in the domain-specific diagram. But this is an extremely high level of abstraction, which doesn't allow us to say much that is meaningful. And so each of these domains includes a domain-specific diagram. And here you can see the generation including DER domain, which is, of course, dominated by power flows. But what's important with this updated version of the model is threefold. Meaningful power is now generated and introduced directly to this distribution system. Customers participate in the solution space, but their primary objective for their resources may be something other than pure generation. And depending on the scale of the resource, it will be introduced at different points within the generation domain, within the distribution domain. These are just some of the important concepts that we're trying to convey with the updated conceptual model. And we do it through a tiered communication structural model. And just to emphasize, we have one of these conceptual model diagrams and descriptions for each domain. I don't expect you to go through these diagrams on this slide, as they're all available in the draft framework, which again is posted online for your review. But the challenge is, what do these concepts mean for interoperability? So to address this question, earlier versions of the framework developed this diagram to graphically depict the communications interfaces between key smart grid systems overlaid onto their conceptual model domain. It's a pretty straightforward representation of what might communicate with what. But for this version of the framework, we wanted to use these diagrams to explore a more complicated set of issues. And so rather than one diagram, we developed a series of communication pathway scenarios like the one you see here. Using the Department of Energy's reference grid architectures for inspiration, we developed multiple communication pathway scenarios to examine the types of network pathways, infrastructure, and information exchanges that might be employed for any one of these scenarios. Here you see our high DER, high distributed energy resources penetration scenario, where internet and IP routable communications are critical to incorporating the many different devices we expect to see deployed and utilized across the system, and the different gateways we should prioritize for normalizing interoperability standards and processes, and even the different and nested control loops that we need to consider as devices and systems exchange information at different levels. And again, I'm going to note that in this framework, we adopt a scenario-driven set of analyses. So we actually have 4 different scenarios that we use to examine how interoperability requirements change for each of these systems. Legacy, high DER microgrid, and hybrid communication pathway scenarios each allow us to explore different concepts and requirements within emerging grid architectures and operational strategies. But with this increasing complexity comes a need for more precise language. As we deal with these 4 different operational scenarios, the ability to understand and describe the differences between them and what we're going after for each of them is really important. And so in this framework, we built an ontology for the grid based on the NIST Cyber Physical Systems framework, which has 9 aspects of a cyber physical system and an associated set of concerns for these systems, right? So in essence, these concerns are the things we care about optimizing in any cyber physical system, the grid included. The aspects of what we optimize, the concerns are how we actually do it, okay? So let's think about the electric grid and how people talk about what's happening. We're making a smart grid where intelligence will move to the edge of the system, right? So what do you need for an intelligent grid? Well, you need sensing and control, otherwise it's not responding to conditions or changing its behavior. It actually wouldn't be intelligent without these capabilities. But for the grid, a control signal alone doesn't mean anything. You actually have to do something. You have to actuate the physical change that your intelligent system requires, and then you have to tell someone or something that you actually did something. You have to communicate. But for a truly intelligent system, you want to understand the physical context of the devices you are controlling, the state of the grid with which you are integrating, and the uncertainty inherent to different resources and aggregated behaviors. You also want to measure the impact your intelligent action had. An intelligent system must understand also the boundaries that constrain the application area, the behavior of the system, as well as the responsibilities of the system. And it must also understand time so that it can coordinate these actions. All of this requires data models that enable the required analysis and accommodates the growing volumes of information in a timely fashion. And you have to be able to build or construct the system to do what you want, and it has to be adaptable to demands that change over time. And in the end, your intelligent grid system has to be usable by humans or it won't be useful. So in this way, through the ontology, what we're trying to do is unpack the specific things we care about that build into the capabilities that we're looking for. And so again, using this cyber physical systems framework, we developed this ontology or dictionary of terms and relationships for the grid that will allow us to be more precise in how we talk about what we want, what we need, and what we are trying to do. When we held our workshops around the country, many stakeholders were really happy about having this reference available, and I encourage you to check it out. The context is in the framework Appendix B. So on to some operation and economic issues. Empowered consumers are at the heart of many ideas in this framework. We talked about that at the start, and it makes things really interesting moving forward. And we spend considerable effort in the framework exploring how the changing dynamic of empowered consumers will introduce new technologies, change operations, require access to and development of new markets, and even affect resilience through the system. But as new technologies are adopted, the dynamics of the system will change. And it's not just in the ways that people typically think. It's because new technologies are overwhelmingly semiconductor-based for generation and consumption alike. This transition not only allows for all the fancy controls that we think of with 4-quadrant inverters and other cool gadgets, but also changes the way that energy is consumed. We don't have time to go through all of the content in the operations and economic sections, but we can highlight a few important issues. So again, I want to give a little context for the adoption of new technologies. Let's talk about the role DERs play in our systems and how interoperability might relate to that topic. So what role do new resources have in the set of operational challenges? Right here you can see some of the inverter functions that were identified in the framework as being required either by IEEE 1547 or California Rule 21. I think what's important to understand is that when 1547 was first published in 2003, there was literally only one requirement, the first, and that was to disconnect from the grid when things went wrong. In fact, by the time 1547 was revised in 2014, only the first 2 functions were required, and a few others were suggested as possible capabilities inverters might want to accommodate. By 2018, when we compiled this list, we found 36 different functions that were either already required by standards, including the new IEEE 1547, or will soon be required by standards. We've got grid following and grid forming, voltage support and frequency support. We've got ride-through and power factor, and normal versus emergency operations. And with the wide open communications and data space allowed by the standards, it's not clear to me that we have a complete understanding of how we should best communicate to fully leverage all of these new capabilities. I'm fairly certain that interoperability has something to do with it because we'll need to find ways to exchange information between devices and systems to observe and manage all of these fabulous capabilities. But we're going to get into that later. So it is, and I guess the real question is it possible that solar PV or other DERs are really responsible for the emerging power quality issues that we see on the grid, right? If you believe our conceptual model, I would say that those resources are still small compared to everything else happening on our system. And to be honest, if you look at the data, right, 1.8% of net generation is utility scale solar. And when you combine utility scale and distributed solar, we're at 2.7% of net generation. So again, the question that we have is it something like solar that most people like to talk about that is driving these changes on the grid, or is there something else happening? You know, so are there other drivers? Is it possible that the change in the way we consume electricity with the introduction of semiconductor-driven loads actually has an impact? So NIST did some work, and it does appear that waveform distortions initiated by the solid-state power electronics in our loads may actually have an effect on the electrical waveform elsewhere in the system. The impacts are minimal when controlled for, however, but observability must be designed to accommodate this changing environment. Information exchange must be equally well designed. For example, the smart meter doesn't transmit the traces, it only shares the valuable information. But moving forward, this elevates the importance of characterizing the dynamics at the interface of AC and DC systems and devices, and it's something we call out in the framework for future work. And I want to make one point about how interoperability allows access to existing market opportunities while also allowing formulation of new opportunities. It used to be that utility resources had to be 100 kilowatts or more to access wholesale markets, and we had to employ proprietary communication systems to interact with utilities. In fact, NIST has a 5 megawatt PV array on campus where we were required to build out a dedicated cellular link to the local utility SCADA system in order to potentially be given the force majeure command to shut down. That was a $40,000 communications expense for a 1-bit communication that we actually hope to never use. Now, not only does interoperability allow aggregation to facilitate market access, and just think of FERC Order 2222 and how that's going to change market access, but interoperability has allowed minimum thresholds of power delivery to be reduced, thereby facilitating market entry for smaller scale resources. But just as exciting as what happens when transaction costs are minimized, full interoperability virtually eliminates the cost of the transaction. This allows even the smallest transaction to be optimized around its actual value rather than the cost of doing business, right? So we think of the difference between EasyPass and toll by plate as being an elucidative example of this situation. In EasyPass, customers go through some effort to obtain the device, provide a credit card or bank account access, and pre-fund their system, so the highway operator is guaranteed funds quickly and efficiently. In toll by plate, the highway operator must take pictures of a license plate, compare it to a universal database, mail a bill, and then process a payment that may come either via direct credit card payment or even a check. In the end, a universal system that lacks seamless interoperability costs a lot more. And the incomplete interoperability of EasyPass, the complete interoperability of EasyPass even allows for a real-time valuation of resilience infrastructures, such as the variable rates of high occupancy toll lanes. So think of what full interoperability could do for transactive energy or anything else in the power system where the value of the infrastructure or the resource may not be constant. Okay, so on to cybersecurity. In the framework, we took two approaches to cybersecurity. The first is to look at securing organizations. The second is to look at securing interfaces. We're going to begin with a discussion of securing organizations. NIST has a few documents and strategies that are great tools to help you think about the cybersecurity needs for power systems in general and your organization in particular. Today, I'll quickly review a bit about the NIST cybersecurity framework and then how we created a smart grid profile for cybersecurity risks based on that framework. And then I'll highlight a few additional resources that might be useful for you. So the cybersecurity framework core establishes a common language for evaluating the cybersecurity posture of an entity or organization. And it also describes desired cybersecurity outcomes organized in a hierarchy and aligned to more detailed guidance and control. This hierarchy is organized along specific cybersecurity functions and then is subdivided into categories within each function, and even further into subcategories that define specific tasks an organization should employ to optimize its cybersecurity posture. And each of those subcategories comes with associated references, right? I know this is getting really confusing, so we're just going to dive in. This is the framework core, and it establishes a common language for cybersecurity. It also describes desired outcomes, is understandable to everyone, applies to any type of risk management, and defines the entire breadth of cybersecurity. It spans both prevention and reaction. You can see that beginning with the identify function, the first thing you must do to secure a system is know what's on it. The core progresses through several functions with associated categories of activities. As you can see within this identify function, we describe that you must know the assets that are part of your system. You must know the business environment for your system and how to address risks, et cetera, et cetera. Then we move to the protect function and the detect, respond, and recover function. Each of these includes categories of activities that will lead to the desired cybersecurity outcomes. And within each of the 23 categories, additional subcategories are defined. And in the cybersecurity framework core, there are actually 108 subcategories. So the subcategories are really where the framework becomes useful because they define the outcomes you're looking for in a secure system. If we dive into the very first category of the identify function, we see that asset management is the first category called ID.AM. It's a pretty simple concept. You have to know the data, personnel, devices, systems, and facilities that are part of your organization. You have to know what you're going to protect. But there are categories within asset management that describe what you need to do. So for example, the first outcome called IDAM1 is that the physical devices and systems within the organization are inventoried. It's a pretty straightforward outcome that serves as a foundation for knowing what you need to protect. But it's not just the hardware. IDAM2 says you need to inventory your software platforms as well. And again, with the 108 subcategories in the framework core that describe the outcomes an organization should seek to achieve and ensure its cybersecurity, and they're all available. And if you have questions about how to achieve that outcome, a list of references are also provided next to each subcategory. So the next question, of course, is how the cybersecurity framework relates to the grid. So NIST developed a cybersecurity risk profile for the smart grid that contextualizes the framework core around specific business objectives for operating power systems, and then describes a set of issues that should be considered when assessing the relevance of each subcategory to the cybersecurity of the system. This framework is also, framework risk profile, this information is also included in the Interoperability Framework Section 5.1 and Appendix G. In our profile, we decided to use these 4 objectives for grid operators to examine the relevance of the framework subcategories and outcomes, right? These are the motherhood and apple pie of the grid. You want to maintain safety, you want to maintain reliability, you want to maintain its resilience, and you want to support modernization. And here you can see a snapshot of what the profile actually looks like. Here we're showing the protect function and access control category of concerns. And then we show the first 4 subcategories or outcomes that a cybersecure organization would be able to achieve. When reviewing this document, you can click on each of those subcategory names, like PRAC3, and it will take you to an online version of the framework core where you can view that specific subcategory. But the important thing are the considerations on the right-hand side of this page. This is where we describe a range of grid-specific issues that a system operator might consider when assessing the importance of a subcategory to the objectives of the organization. This is where including this in the framework gives anybody who's just gaining an introduction all the way up to somebody who is trying to use the NIST framework to manage the cybersecurity risks to their organization, the information necessary to have the hard conversations and prioritize these subcategories and their resources against them. So one more thing here, in this implementation, we also used a binary assessment of subcategories, and each one you see highlighted in purple means we determined that outcome is relevant to the objective listed above, right? You can see that given the very high level objectives we described, most of the subcategories are relevant to all of the objectives. But the considerations that we provide can be used by somebody looking to use this for their organization to evaluate their cybersecurity posture against their specific objectives. But even where a subcategory breaks from this pattern of everything being relevant, we can really learn something. So here you have PRAC6, and we believe that it's not just not applicable to securing the grid. So when you look at that subcategory, the core says the outcome should be identities are proofed and bound to credentials and asserted in interactions. So this is a very basic requirement and really a gold standard for securing system. Any organization should want to know who is on their system and what changes they've made. But we think that's not necessarily possible on the grid, right? Why? Well, in the United States, utilities often assist each other in responding to and recovering from natural disasters. So introducing a requirement to achieve this outcome may mean that assistance from cooperating utilities would be delayed until assisting workers from other utilities could get badged into the home utilities identity management system and trained on how to interact with it. And that impact on recovery would not be helpful. So in this example, you see how the considerations we've developed help us think about the cybersecurity functions categories and subcategories of the framework core. Also, just in July, NIST and NERC posted a new tool on the NERC website. So when you look at this NIST framework and then you compare it to NERC SIP, it's not always clear how the NIST framework functions, categories, and subcategories relate to the 16 different NERC SIP standards that either are enforced or soon will be. So we created a mapping tool that is based on our risk profile, which is included in section 5.1 in the appendix of the framework. And we've posted it on the NERC website. You can see, if you go to the NERC one-stop shop, you can find the link. And if you go down to where that yellow arrow is at the bottom, where it says, NIST, you can download that mapping tool. It's actually really powerful. It's got a pivot table in the back, so you can organize everything based on either which NERC SIP standards are relevant to which to each NIST cybersecurity subcategory, or you can flip it and you can which subcategories are relevant to NERC SIP. It's a really useful tool, and I encourage you to go on and try and find it. Now, logical interfaces. This is how we deal with protecting information exchange of the individual interface, right? There's one thing to secure an organization. There's another thing to try and secure specific interfaces, right? So we're going to begin by looking at the logical interface categories of NIST 7628, and then look at the high DER scenario that we developed in the framework. So NIST and our industry collaborators took the conceptual model from earlier frameworks, in this case it was actually V3, and thought about which actors in the system would benefit from secure interoperable communication. In fact, they identified about 50 different actors on the system, grouping them by NIST conceptual model domain. And while this helps you see who has a role in making the electrical grid work, it doesn't help us understand who they communicate with and how. So the authors put their heads together and tried to figure out who would need to communicate together and why, and they came up with this diagram that is affectionately or pejoratively known as the spaghetti diagram. And NIST and our industry colleagues looked at all of those interfaces and came up with yet another table. The important thing here is that each of the communications or logical interfaces shown in the 7628 spaghetti diagram could be grouped by their functional characteristics. And in the end, the 2014 guidance indicated there were 22 different categories of logical interfaces, and protection schemes and best practices could be somewhat normalized for interfaces within each category. NIST 7628 did a great job examining the system interfaces across the grid, but as we have discussed, architectures are changing, and a persistent fear among many stakeholders is that these new architectures present new and uncharacterized interfaces and security risks. So we updated the NIST 7628 diagram just a little bit, and in the framework, we evaluate the high DER scenario and examined how interfaces for the various actors and systems would evolve with new technologies and resources. We added certain systems like DERMS and Bach25 that replaced some lesser functioning actors in the previous model. And finally, we split up the end-use devices to clearly indicate actors like control and comms units, where the communications would be transmitted external to the device or function, and those parts of the system that would only receive internal communications, mostly by way of low voltage control signals. So here you can see the result of our analysis. Every blue interface is an existing interface from NIST 7628. Every red interface line is a new interface that wasn't included in the earlier work. At first glance, it does appear that the new connections could overwhelm the interface and security concerns of the system, but we also examined how these new interfaces relate to the existing logical interface categories as defined in NIST 7628. What we determined was that while there are a large number of new system interfaces, the characteristics of these interfaces can be grouped, and so the logical interface categories and associated security requirements can be mapped to existing logical interface categories, LICs. So this means that despite the newness of the interfaces, we can still draw from existing knowledge and protection schemes. And in the back of the document, there's another appendix that illustrates exactly why we grouped each of these new interfaces in the existing logical interface categories. Okay, So on to testing and certification, and there's a lot of activity happening right here. We're going to run through this section, the early part a little bit quick because I want to get to this interoperability profile content. This is a big important outcome, and NIST has a big push in the community to work on these interoperability profile ideas. So standardization is key to increasing interoperability, right? This reduces the time and resources necessary to introduce new technologies while enhancing overall functionality. I want to dive into the interoperability feature space and examine how we can facilitate a high level of interoperability. So we're going to start with a physical function, right? What you're trying to do with a device or system is critical to understanding how we have to communicate about it. The interoperability profile would look different for a thermostat or an inverter or a microgrid controller, and it honestly may even look different for a single device used in 2 different applications. Then we need to consider the communications protocol. So if you imagine the communications protocol as the envelope in your first class mail, right? It gets your information where it needs to go, and it has some constraints, right? Like you can't ship a Harry Potter novel inside a letter envelope. But within that constraint, these protocols can get any information anywhere you want it to go, just like you can send a letter anywhere you need it to go. And in fact, if we take this shipping company analogy a bit further, we can say that the difference between the Postal Service and FedEx and UPS and DHL and the companies that move things like shipping containers around the world is analogous to the different communications protocols. They each have different purposes, different latencies in their shipping speed, and different capacities in their envelopes or shipping containers, right? But the information or data model is different from the communication protocol, but equally important. The information model is what we use to convey the information inside the envelope. It's the language and the grammar and the syntax that allows us to meaningfully communicate with one another. From an interoperability perspective, specifying an envelope without content is just as worthless as specifying the content, but not the shipping mechanism. Because if you can't get the information to another device or system, the value of working together simply doesn't exist. But the ability to combine all of these standards relating to the physical function, communications protocol, and information model in many different ways leads to a combinatorially complex space, which we show here, and where each of these clouds represents one potential approach to interoperability. So, now let's consider the IEEE 1547 case study. And before we do that, actually, I want to talk about this. We did a standard landscape analysis that fed into the framework. It's both in the framework and in the separate tech note. We looked at 240 standards that were identified by other groups as being relevant to smart grid. We deemed 169 of them were relevant to these 3 pillars of interoperability that I just described. Only 21% of these standards have third-party testing and certification available, and of those, the vast majority are for communications protocols. Now, if you think about randomly combining this complex feature space and standards from each of them, if each standard only has a 20% probability of having testing and certification associated with it, you have less than a 1% chance that the different hardware functional requirements, communications protocols, and information models you're specifying could actually be verified via a testing and certification regime. So now let's consider that example of the PV inverter, right? So do you remember all those inverter functions we discussed a few minutes ago? So the 2018 update of 1547 defines most of these inverter physical capabilities as required for standard conformance. And in my opinion, it is one of the most important standards in the world because if properly managed, these capabilities will revolutionize the way PV and other inverter systems interact with the power grid. But 1547 is also pretty poor from an interoperability perspective, because the standard allows conformance if an inverter can communicate by any one of 3 communications protocols. And although each of these communications protocol standards also has an information model associated with it, 1547 is silent on when or how to choose which information model. And to top it off, section 10 of the standard says, by the way, we really like the 61850 data model that wasn't related to any of the required communications protocols. So just from that, you have 12 different potential interoperability profiles where a device could conform to IEEE 1547. And because of that complexity, nobody has put together a certification test for this standard. Compare that to California Rule 21, which identified the inverter function, said the communication protocol had to be SEP 2.0, and the information model had to be IEC 61850. The result was the equivalent of a single interoperability profile that led to the creation of a testing and certification standard and program under UL 1741 SA, right? It's pretty simple. When you work with industry and reduce the implementation optionality, you can achieve interoperability. And so NIST is actually working right now via the Smart Electric Power Alliance and a cooperative agreement that we've established with them on multiple interoperability profiles. This is beyond standards conformance, and we're working to ensure interoperability via these profiles. We have two sets of activities right now. The first is for managed charging of EV fleets to provide grid services, and the second is for interoperability profiles for distributed energy resources. The second one, the DER profile activity, is really just starting right now. So if you want to get involved in it, it's the perfect time. I've got the link there at the bottom of the slide. You can just Google SEPA interoperability profiles and you can get to that page and you can find out how to become involved. What we intend to have put out from these activities are use cases, application guides, and the specific requirements that would make the interoperability profile. Okay, so thank you for your attention. I think I hit 45 minutes on the nose. Please go to the NIST website and download the draft framework. The link is on the left. You can also go to the Federal Register announcement from September 18th, where we describe the public comment process and timeline. Comments are due before 5 p.m. Eastern on November 2nd. And so with that, maybe we can have some Q&A.
Hey, Avi, I want to, first of all, thank you very much for giving us this wonderful presentation. I feel even I have read some of your version 4 framework, I feel there's a lot of information. I'm trying to catch up with your flow. So great job, done by you and your team.
Thank you.
So yeah, we do have some time for Q&A. Olivera, if you're still online, can you take over and to see what question we have or get the audience questions as well? Thank you.
Yes. Yeah, thank you, Avi. That was a wonderful talk. I learned so much, but as Henry said, it's hard even to take a note. You share so many information. So from my side, I'm curious. So if someone who just wants to get familiar or to implement some of the standards, interoperability standards, so what will be the best way to start with or to pay attention? Yes, what advice you can give to?
So if you're just focused on the standards relevant to the smart grid, you could skip right through to section 6 of the framework. That's where we describe the testing certification landscape and the relationship between standards and interoperability. I think that's a good start. The way we wrote the framework was that the document should be fairly accessible. We have, I think the content is about 90 pages. The appendices are maybe 120, right? So we try and distinguish between the language and that we can use to communicate with everybody and the technical details that are stuck in the back. We also organize it again on these themes, right? It's introduction, and then these models to help you understand, and then operations and economics and cybersecurity. But if you're really just thinking about standards and testing and certification and interoperability profiles, that's its own separate section at the end, section 6. And I think you should be able to read it sort of in isolation of the rest of the documents and still get something meaningful out of it.
Okay, thank you. Does anyone else have any question? Oh yes, we have one in the chat. Is there any standard communication and modes of communication defined for islanded microgrid, especially for primary, secondary, and territory control?
Well, so there is an IEEE standard for microgrids, it doesn't get to the level of what you're asking for. That would be IEEE 2030.7. And then IEEE 2030.8 is essentially the testing standard for the microgrid controls identified in 2030.7. I will tell you very candidly that NIST has been working to try and implement some of the 2030.7 use cases in our test bed, and we have found that the standard is very underspecified for that need. It's not a straightforward translation from the functions identified in 2030.7 into the things that we would want to implement and validate performance. So there is that standard, but it doesn't get to the level of specificity that you are looking for. There are other standards for communications. IEC 61850 is a beast to understand, but it's very useful, and they have working groups and logical nodes that can be used really for almost any type of implementation. The challenge with 61850 is that really you need to have a master's degree in that standard alone to understand it and work on it. But really all of the communications protocols, right, SEP 2.0 or other things like that, SEP 2.0, sorry, is 2030.5, can be used for these types of controls. And that's why we're talking about, you know, the difference between a communications protocol and a physical activity, if you think of those three legs of that stool.
Okay. Thank you. Okay, another question we have, how the inverter manufacturer complained with different combination of communication protocols and information models like UL 1741SA, if they vary across the country's states?
Yeah, so that's a really important question, and that's why we've started our DER profile activity. There are tests and certifications for the physical functions of 1547. And as a matter of fact, I think 1547.1 was just balloted and implemented in the past, I think, half year. And 1547.1 is the test protocol, again, for those physical functions. But even IEEE's own test standard doesn't go after the communications protocols. And that's a real challenge. That's why we're working on this, because a standard can be conformant to 1547 if it uses Modbus or SEP 2.0. You know, there's all these different protocols that could be used. And so nobody right now has a test in place to evaluate that, except for, again, UL 1741 SA, but that's not related to 1547. That's related to California Rule 21.
Mm-hmm. Yes, and then we have just thank you in the chat from Koti Reddy from Department of Atomic Energy from India.
Oh, thanks very much. Appreciate it.
Okay. Does anyone else has a question?
Hey, Javi, if you don't mind, I would like to ask a quick question.
Yeah.
If I read the version 4.0 right, I haven't finished yet. I'll be honest, I'm still reading. I feel you made DERs much more visible compared to the previous version. And then plus, you already mentioned in the FERC 2022 also, I would say, create a major milestone for DERs, you know, finally allow them to be in the market. So and then also, of course, DERs is being developed in the real system and so on. So a lot of efforts going on. So with all this being going on, and also in the FERC order, and also your, you know, framework can also drive in that. So what is the future of DERs in your opinion, and then how they will evolve and help the grid, or like a fully functional to be in the grid system?
Yeah, so it's a great question, Henry, and I think there's an inexorable trend towards DER, right? Now that we have solid state power electronics that can do all of these amazing things, the cost of solid state power electronics are coming down, right? Now, power system devices and equipment are on a semiconductor cost curve, not the big industrial cost curves of steel production and things like that, right? We're on a semiconductor cost curve now. That changes the cost structure, the cost curves, the learning by doing all these other things. So they're going to continually get less and less expensive. And semiconductor-based devices, semiconductors are fully modular, right? So just like we have massive computers that rely on thousands and thousands of cores and things like that, you can have a semiconductor-based set of equipment that can either be small, like an individual PC, or huge, right? And they all use the same foundation. And so what that means is that the best capabilities are going to trend downward into smaller devices. And people are going to buy them and use them to take advantage of all of these amazing capabilities. Now, what that means for the future of the grid is a little bit uncertain. And that's where I'm directing NIST's research to really examine some things. Not included in the framework is the work that we're doing to build off of some of these questions we have about the interface of AC and DC systems and devices. So we actually just submitted a paper to ISGT on characterizing the impedance of residential home circuits, right? And why do we want to characterize the impedance of circuits? Because at the same time as we're characterizing the circuit level harmonics and transients from not only from LEDs, but from other appliances and miscellaneous electrical loads, we want to understand, how does that propagate? Does it actually make it out of the house circuitry? Can it go beyond the point of common coupling? How does it get through a transformer, and what does it look like? Because we don't want to look at just the fact that there's some pretty tough harmonics showing up in certain places on the grid. We want to know, where are they coming from, because that changes what the requirements should be for managing it. So that's work that we're doing right now, and that we hope to use to inform the next framework or set of framework activities, where we can define what a set of requirements might look for now that we have a better understanding of these interactions. The thing about impedance, which I'm a mechanical engineer by training, right? I mean, if it's a hammer and a wrench, I got it. This stuff is a little bit wild to me. But the fact that just connecting the device to the circuit changes its impedance, which then changes the way that the transient is going to propagate through the system, right? It's incredibly complex. And so we need to use NIST's research to build the envelope around what these things are doing on the system, so that we can understand the range of considerations that we have to work on.
Mm-hmm.
Yeah, I think that's a great view. I fully agree with you. Power electronics be a critical piece of the whole thing. I'm kind of like you. I'm a power system engineer. Look at the big transformers, big power lines, but this power electronics all happen at a micro level, microsecond, and also small electrons, right? So I fully agree. I think looking forward to the further work you're going to publish and learn more from those two aspects.
Yeah, thank you very much. What's interesting is this work that we've just submitted, right? We identify where the knee in the curve is, right? Yeah. We identify where the circuit behaves like a resistive circuit, and where it transitions to being where the capacitance and inductance of the circuit take over the behavior. And so the important thing is that when we look at our current standards for power quality, the range of frequencies that they work in are really when these systems these circuits are in their resistive range. But we have this whole other set of response characteristics that may or may not have an impact on what we're seeing elsewhere in the system, but also have but occur outside of our THD standards for power quality. So it's quite an interesting space, and we're really doing the work necessary to not only characterize the parameters, but evaluate and assess the relevance of those newly defined parameters to the real world system.
Yeah, thank you. Back to you, Oliver. Sounds like there's another question in the chat window.
Yes. So Avi, if you have a few minutes more, we have another question in the chat, if I may ask. Okay, so is it possible to effectively coordinate the DERs and conventional distribution system assets using the current communication protocols, considering the uncertainty in PV and other loads?
Yeah, so this is an area of active research at NIST. What we've done is we've published a few papers on new on governor-based control theory for individual inverters, and what we're trying to do is apply those theories to examine the networked behavior of these devices, and how we might look at emergent behaviors via conventional control paradigms versus some of these new control paradigms, and then relate that to the different communications protocols. At this point, I'll tell you that each of these inverters essentially operates locally, right? You can tell it which way, which function you want it to perform from any one of those dozens of IEEE 1547 functions. But to coordinate it beyond that, right now, there's not a standard way to do that. And we're working on whether that is necessary, how much it could improve the system versus what might be needed or not. I'll tell you that for this experiment, we're actually installing a 30 kilowatt bifacial PV array on the NIST campus that ties in directly to a bus that has some large industrial loads on it. And we have a couple of inverters that we tied to that 30 kilowatt array. So we can understand the latest in technology and how how emergent dynamics and behaviors might evolve on the system based on these different control schemes. But it's going to take us a while to get through this work, unfortunately.
Okay, thank you. Yeah, there is a thank you for Krishna that asked that question. Yeah, a lot of appreciation from our visitors to your work, Avi. So thank you so much.
Well, thanks very much. It's been great talking with you. Please, head to the website, download the document, get us your comments before November 2nd, and then we'll have our final version published sometime early next calendar year. So thanks, everybody. Appreciate your time.
Avi, thank you again for giving us a talk. I think given this virtual format, you don't see the faces, but I'm sure many of them are just like me, nodding their heads, So I really appreciate your time and sharing your knowledge today. I'm sure we'll be in touch again. I will continue to read the version 4 framework and may have a question for you later.
Great. Thanks, Henry. Look forward to talking about it.
Yeah. Thank you, Avi.
Bye-bye.
Yeah. Thank you, Avi. Everyone have a good rest of the day. I appreciate so much, Avi, for finding the time to. We negotiated for quite a while you to be one of our speakers, but we finally managed you to join to our webinar series. So I appreciate a lot, and I know this is end of the fiscal year so for many people it's very hard. End of fiscal government year. Yeah. So as one of my colleagues today said, happy new government year.
Thanks very much. Appreciate all your time and effort in helping me work through the tech challenges we had. I really appreciate it. So thank you.
Thank you. Thank
Thank you.
you.
Bye-bye,
Bye.
Avi.
Bye.